Yes, let's continue this. We have ethanamine, ethanol and methanoic acid of almost comparable molecular masses 45, 46 and 46, and I have seen we have found their boiling points, right? So this shows that amines, alcohols and carboxylic acid of comparable molecular masses, carboxylic acid has the highest boiling point, then alcohol, and the least is that of amines. So I am again repeating here, though they have two NH bonds, it seems like they have more extent of H bonding, but as this bond is less polar as compared to OH, so alcohols are having higher boiling point as compared to amines, right? So this is a very important comparison. Clear? Okay. Now next physical property we will discuss is solubility. Fine. So third we have solubility. Fine. Now primary, secondary as well as tertiary amines, rather lower amines, they are soluble in water due to formation of H bonding with water molecules. Fine. And we know here also on the same basis that primary have 2 NH, secondary have 1 NH bond, and tertiary have no NH bond. So as a result they have more extent of H bonding with water. I am just representing their H bonding with water. So like that you can represent it. Fine. It can be extended with this hydrogen also, water, and then more extension toward this side, more extension this side, here also with water. Fine. So this is partial negative, partial positive, negative, partial positive. Sorry, here with oxygen it has to be, here it will be with nitrogen. Fine. And like that. Fine. Partial negative, partial positive, negative, right? Like that, so on. H bonding extent will be there with water molecules, right? So more NH bonds are there, more will be the extent of H bonding with water, so more will be solubility, right? So among comparable molecular masses, primary, secondary and tertiary, if comparison is asked, primary are more soluble than secondary than tertiary, right? Okay. Now this is one comparison. Secondly, if we have comparison among same class, that is primary, secondary or tertiary, among same class. Suppose we have primary. If I make a comparison among these are the lower members of primary amine. These are highly soluble in water. But if I keep on increasing the length of the chain, then it's true in all primary, secondary or tertiary. If the size of the alkyl part, this is the alkyl part, if the size of the alkyl part goes on increasing, then it becomes a retardation to form H bonding with water. That means if the size of our group, if this is a bulkier group like that, then there will be less approach of water towards NH. Fine. So as a result, bigger the size of our group, less is the solubility. So solubility in this direction decreases as the size of our group goes on increasing in any primary, secondary or tertiary amine. Fine. So this is regarding solubility of aliphatic amines. Now one more, aromatic amines. Among aromatic, for example, aniline. Aniline is almost insoluble in water due to presence of a bigger aromatic group which hinders H bonding with water. Fine. As a result, what happens? the compound is not soluble in water, but aniline is found to be soluble in organic solvents like that. For example, carbon tetrachloride, chloroform, etc., ethers, etc. So it is soluble in organic solvent, but it is soluble in water. So this is regarding the solubility of amines. We were discussing the physical properties of amines. Now we'll shift to chemical properties of amines. Chemical properties, that means when they interact with other substances. Fine. So first, the most important for them is their basic character. Basic character of amines. We'll discuss basic character of both aliphatic as well as aromatic amines, and remember, this is very important for examination point of view. Usually one question will be asked from this topic, right? Now, basic nature. Suppose when primary amines are treated with water, first suppose the reaction with water, then because of presence of lone pair, they can attract this proton, right? They can accept a proton from water. So they are accepting a proton, therefore they will act as Bronsted base. Fine. So as a result, they form NH3 positive plus OH negative. And moreover, you see, as a result of this reaction, they release hydroxyl ion in solution, which also shows their basic character. Now, presence of this hydroxyl ion can be checked if we treat this with aqueous solution of aluminium chloride, and you will get gelatinous white precipitates of aluminium hydroxide. This is experimental justification of presence of OH negative ions, which are given when amines are added to water. Fine. So this shows the presence of a lone pair on the nitrogen is the basic cause for accepting proton. Fine. Okay. Now let's do their reaction. If they are bases, they might form salt with the acids. For example, we have here RNH2, one very important reaction here. When this is a general reaction, reacts with HCl, so proton is there. Just to understand, I have put this sign, otherwise, so like this, so it will be RNH3 plus charge, because nitrogen have donated its lone pair to the proton, and Cl negative. So you will get this salt. Fine. Or primary as well as secondary. Suppose I have this secondary, suppose it reacts with nitric acid. Fine. Then you will get here R2N, one H is increased, it is H2 positive, NO3 negative. Fine. It may be R3N, a tertiary amine can also act. Suppose the acid is now sulfuric acid. Fine. So one H is gained, so it is R3